On the morning of the 27th of May, 2026, just 4 days before the official start of the Atlantic hurricane season, a vast plume of tropical moisture is lifting out of the Caribbean and moving north. It is advancing over a nation that has just endured its driest January to March period in 131 years. After 181 days of waiting, the atmosphere is finally delivering a cure for the parched landscape. Yet, this very same body of moisture is being closely monitored by the European Centre, the US Operational Ensemble, and Google DeepMind for potential tropical development within the first 10 days of June. Herein lies a profound paradox. The cure and the threat are born from the same air mass, and the country below has no choice in the matter. When the rain that could break a modern record drought arrives in the same system that might become the first named storm of the season, what does this convergence signify? This is the kind of complex question we seek to understand here at CalmSpace, by focusing on the patterns revealed in the data itself, rather than on social media hyperbole. Let us now examine the event as it unfolds, piece by piece, to see the larger story taking shape. The story of this first drought relief of 2026 begins with a single, tangible event. At 9:32 inches the morning, on May 27th, a weather station at Port Isabel Airport on the southern tip of Texas recorded a wind gust of 61 miles per hour. While such a gust is not unusual for a late May thunderstorm on the Gulf Coast, its significance lies in what it represents. This gust was the leading edge, the very front door, of the deepest pool of tropical moisture to emerge from the Caribbean this year. It was the arrival of an air mass that had spent days over the Western Caribbean, absorbing immense amounts of water from an anomalously warm sea surface. Finally, a digging upper-level trough reached down, grabbing this moisture-laden air and pulling it northward. As the gust struck Port Isabel, the consequences began to ripple outward. The National Weather Service office in Brownsville issued a severe thunderstorm warning for southeastern Cameron County, citing radar-indicated winds of 70 miles per hour. That same warning was soon reissued for another cell over the port of Brownsville. By late morning, the impacts had spread far inland, with a flash flood warning active for Dallas, Kaufman, and Rockwall counties in Texas. Hundreds of miles away, another was in effect for Fairfield, Franklin, and Licking counties in central Ohio, where 2 to 3.5 inches of rain had already fallen, with more on the way. A third warning covered the spine of West Virginia. By mid-morning Eastern Time, the national alert map for the contiguous 48 states showed 363 active alerts. This data paints a picture of a nation experiencing a complex, multifaceted weather event. While 241 of these were small craft advisories, mostly for Alaska and Pacific marine zones, the map also included 26 flood warnings for rivers and creeks, 11 flood watches, and 4 imminent flash flood warnings. The country was being impacted on 3 distinct fronts simultaneously. Tropical moisture from the south, a stalled boundary on the eastern face, and an upper-level low on the far western face, which the Los Angeles NWS office described with stark, bureaucratic understatement as unusual for this time of year. Yet, to focus only on these alerts and satellite loops is to observe the event from the outside. The true story, the deeper meaning, is found in what this system is actually delivering to the ground. For the first time in 5 months, what is arriving is rain. This moisture is falling upon a landscape gripped by a drought of historic proportions. The numbers we have examined previously paint a stark picture. 62.42% of the contiguous 48 states in drought conditions, affecting 158.2 million people across 46 states. The period from January through March of 2026 was the driest such window in the 131 year as statistical record, a record that dates back to 1895. It surpassed a mark that had stood since 1910. Furthermore, the Palmer Drought Severity Index for March 2026 was the highest for any March on record, and it marked the third driest single month of any season ever recorded. The only 2 months that were drier were July and August of 1934, the climatological peak of the Dust Bowl. To be ranked just behind the worst moments of the most infamous drought in modern American history is to understand the gravity of the situation we have been living in since January. This atmospheric crisis has been mirrored by a structural one in the nation's water systems. The Bureau of Reclamation's the 15th of May 2026 4-month study projected that Lake Powell could fall below the elevation needed for reliable electricity generation at Glen Canyon Dam as early as December. Compounding this, the 2007 interim guidelines that have governed the lower Colorado River for 18 years are set to expire on December 31st, with no replacement agreement signed. Meanwhile, Phoenix is under a Stage 2 drought response, Georgia is on a statewide Level 1 response, and the vital Ogallala Aquifer beneath the Texas Panhandle is on a multi-decade path toward becoming unusable. These are the dominoes we have seen lined up. This confluence of events leads to a critical question. What does the initial phase of a systemic failure truly look like? It begins not with a sudden collapse, but with a powerful, ambiguous shift in the atmosphere. Before the legal battles intensify, before the hydropower capacity is lost, and before another year of agricultural failure can compound, the weather pattern itself finally moves. The drought does not simply end. More precisely, it begins to break. As this story is told, the first meaningful tropical moisture surge of 2026 is arriving. It will continue to sweep across the North Gulf Coast, Florida, the Southeast, and the Ohio Valley, right through the official opening of the hurricane season on June 1st. From Cancun and western Cuba, across the Cayman Islands and Jamaica, and along the entire expanse of the North Gulf Coast, from Brownsville through Mobile and Pensacola, and over the entirety of Florida, a single, vast weather system is delivering both relief and a warning of what is to come. For the people of Georgia, Alabama, Mississippi, and Louisiana, and across portions of South Carolina and its hinterlands, a long-awaited rain is finally approaching. This marks the first significant rainfall of the calendar year, but it is crucial to understand what this event truly represents. This rain does not signify the end of the drought. It would be a disservice to suggest that in 2 weeks, the U.S. Drought Monitor map will be clear. A drought of this magnitude and persistence cannot be undone by a single weather event. Recovery demands months of above-average rainfall. The vast hydrologic system does not reset in 72 hours. Reservoirs will not be replenished by one storm, nor will soil moisture return to its normal state just because the skies have opened. Instead, what this rain offers is the beginning of a recovery. It arrives at a critical juncture. Just as the drought was poised to enter its 6th month of structural deepening, it comes before the climatological peak of fire season and ahead of an agricultural calendar that threatened a worst-case scenario for winter wheat and cattle herds. The drought is not over, but after 181 days, following the driest January to March period in 131 years, it has finally begun to end. To understand what is happening, we must look at the atmospheric mechanics behind this shift. The meteorological setup is key to grasping the full story that will unfold. Currently, a deep upper-level trough, a significant southward dip in the jet stream, is positioned over the western United States. On a 500 millibar height map, this feature appears as a pronounced U-shaped channel of low heights. This trough has been extending southward through the Great Basin and reaching into the Bay of Campeche, the distinctive B-shaped body of water in the southwestern Gulf of Mexico. The jet stream, that powerful river of air flowing at roughly 30,000 feet, is dipping into this trough and plunging down toward the Western Caribbean, drawing tropical moisture northward with it. Working in concert with this trough is another major atmospheric feature, the Bermuda High, parked over the southwest Atlantic. This is a semi-permanent subtropical high-pressure system that typically anchors itself east of the southeastern U.S. In late spring and early summer, as it strengthens, it begins to pump warm, humid air northward along its western edge. The combination of these two systems, the trough pulling moisture from the south and the high pushing it from the east, creates the powerful engine driving this weather event. It is a perfect, large-scale atmospheric machine for transporting immense amounts of moisture. The tangible result of this setup is staggering. This morning's 12 UTC sounding from Sterling, Virginia, measured a precipitable water value of 1.82 inches. If you are unfamiliar with the term, precipitable water is the total depth of liquid water you would have if you condensed all the water vapor in the atmospheric column directly above you. A value of 1.82 inches is something one might expect in a humid southeastern air mass in late July, not on the 27th of May over the mid-Atlantic. This single data point reveals an atmosphere behaving far outside its seasonal norms. Further analysis from the National Weather Service office in Miami confirms the extremity of this event. Examining the latest GFS model data, they described the total precipitable water anomaly for this morning as being approximately 3 standard deviations above the seasonal mean, with some model values exceeding 2 inches. In a normally distributed climatology, being 3 standard deviations above the average corresponds to the 0.3% statistical floor. This means an event of this magnitude is expected on only 3 out of every 1,000 May 27ths in the modern record. The atmosphere is currently saturated with a level of moisture characteristic of tropical summer 4 days before the Atlantic hurricane season even officially begins. Consequently, the Weather Prediction Center, the national authority for forecasting heavy precipitation, has issued a slight risk of excessive rainfall. This is a level 2 on their 4-level scale, covering a wide swath of the Gulf Coast from eastern Texas, across southern Mississippi, and into the far southwest of Alabama. The outlook specifically flags the potential for scattered instances of flash flooding, a primary concern, as noted in the outlook text, is the condition of the ground itself, which is already saturated from rain over the past few days. This concern extends northward. The center has issued a second, parallel slight risk that covers parts of the Ohio Valley and the central Appalachians. The logic is identical. Recent rainfall has left the soils increasingly saturated, elevating the threat of flash floods wherever today's storms might cluster and intensify. The stage is set for water to run off rather than soak in. The situation on the ground is already escalating. The Houston NWS office, in its morning forecast discussion, described a slow-moving line of strong to severe thunderstorms advancing across southeast Texas. They are forecasting rainfall totals of 1 to 2 inches, with the potential for localized pockets receiving up to 5 inches throughout the day. Elsewhere, the Brownsville office has entered a warning phase. The Wilmington, Ohio, office is in a warning phase. The Charleston, West Virginia office is also in a warning phase. By the time evening news broadcasts air tonight, the nation will be looking at a continuous corridor of heavy precipitation. This band will stretch from South Texas through central Mississippi and extend all the way up into the Tennessee and Ohio valleys. This is how the breaking of a drought begins, not with a gentle, soaking rain on a calm day, but with something far more forceful. The first significant precipitation to fall on a drought-parched continent is going to be hard, because that dry, hardened land cannot absorb water the way a normally hydrated landscape does. We will explore this aspect further in the second part. For now, it is vital to hold on to the central thread of this narrative. The true story here is not the drought, nor is it the storm. Instead, our focus must turn to the air mass itself. This specific body of moisture, lifting out of the Western Caribbean today, will spend the next 4 days laying a blanket of rain across the parched southeast and Gulf Coast. It is being watched by every major weather model in the world, not just for what it is doing now, but for what it might do the moment hurricane season officially opens. This air mass is the protagonist of our story. Everything that follows is about what it does next. What it is doing right now is delivering a cure. What it might be doing in 4 days is something else entirely. Let us now return to a phrase used by meteorologists. 3 standard deviations above the seasonal mean. It is worth pausing on this number because it is the kind of technical term dropped in a morning forecast discussion that should make one stop and put down their coffee. It passes by because few outside the meteorological community are there to translate what it truly signifies. To understand its weight, we must look at basic statistics. In a normally distributed data set, and atmospheric variables like precipitable water are quite close to this, we find a predictable pattern. Roughly 68% of all values fall within 1 standard deviation of the average. About 95% of values are found within 2 standard deviations, and approximately 99.7% of all recorded values lie within 3 standard deviations of the mean. This framework is the key to understanding just how rare the current atmospheric conditions are. The atmospheric conditions reported by the Miami office this morning are a true statistical outlier. An event registering beyond 3 standard deviations from the norm falls within the bottom 0.3% of all historical data. To put that in perspective, the amount of moisture currently laden over Florida and the Gulf is something that, statistically, occurs on only about 3 out of every 1,000 May 27 deaths in the modern record. If you were to choose a random May 27th from the last 45 years, you might find this level of atmospheric moisture on 1, perhaps 2, of those days. Today is one such day. But this isn't just an impressive number on a graph. Its significance lies in its physical meaning. A value of 2 inches of precipitable water indicates that the entire column of air above you, from the ground to the top of the troposphere, holds the equivalent of 2 inches of liquid water in vapor form. When a lifting mechanism, be it a weather front, a sea breeze, or a convective system, squeezes that atmospheric column, it can release up to 2 inches of rain onto the ground. While the process is never perfectly efficient, a tropical air mass can achieve a precipitation efficiency of 75% to 90%. So, when forecasters warn of rainfall totals reaching 2, 3, or even 5 inches per cell, those figures are derived directly from this available water budget. The atmosphere is carrying the potential for a deluge. The only question is how the ground will receive it. For much of the southeastern Gulf Coast and the Mid-South, the answer is badly. It is tempting to view drought-breaking rain as unequivocally good news, but the reality is far more complex. This precipitation is certainly necessary and long overdue, but its arrival after 181 days of drought creates a unique set of challenges. A landscape that has been baking for half a year will not respond to this rainfall in the same way a normally hydrated surface would. The ground itself has been transformed by the prolonged absence of water, and this change will dictate everything that follows. The underlying mechanism is well understood and documented in climate science literature. A 2019 paper by Males et al., published in the Times Proceedings of the National Academy of Sciences, quantifies how soil moisture, or the lack thereof, couples with the atmosphere to influence extreme weather. The central finding is that dry soils amplify local atmospheric responses in ways that wet soils do not. This principle is most often cited in the context of heat. Because dry soils lack the water needed for evaporative cooling, they cannot regulate their temperature through latent heat flux. Consequently, the air layer nearest the ground heats up more rapidly and reaches higher peak temperatures, which helps explain why drought-stricken regions often set new heat records. We have explored this very concept here on Calm Space in previous discussions. However, this same mechanism has a perilous downside. After 181 days of dryness, the soil has lost much of its ability to absorb water at a normal rate. The structure of the upper soil column has compacted, and in many drought-prone areas, hydrophobic crusts have formed on the surface. This phenomenon, known in soil science as surface sealing or crusting, is well documented in agricultural studies from the Great Plains to the Mediterranean. It creates a tragic paradox. The very rain the land so desperately needs is unable to penetrate it. When the first significant rainfall hits this compacted, crusted surface, the rate of infiltration is drastically reduced. Instead of soaking into the soil, the water is forced to run across the surface, seeking the nearest low point, stream, or river. The runoff coefficient, which measures the fraction of precipitation that becomes surface runoff instead of infiltrating the ground, can be 2 to 3 times higher on land that has been primed by drought. In practical terms, this means that the same 1 to 3 inches of rain that might cause moderate, localized flooding on a typical late May day will now produce disproportionately severe and faster rising flash floods. This is not merely a forecast. The effects are already appearing in real-time river gauge data across the region. The flood warnings, active this morning, are not for gentle, multi-day rises, but for dangerously rapid surges. Near Corpus Christi, Oso Creek is projected to crest at 23.9 feet this morning, recede to 12.9 feet by evening, and then rise again on Friday, a clear flash response, not a slow-moving flood. Elsewhere, the Wolf River above Gulfport, Mississippi, is in moderate flooding, with water encroaching on residential properties at 12 feet. The Pearl River, along the Louisiana-Mississippi border, is in minor flooding and continues to rise. Similar minor flood warnings are in effect for the Jordan River near Bay Street, Lewis, the East Hobolochito Creek in Mississippi, the South Fork Sabine River in Texas, the Saluda River in South Carolina, the Calcasieu River in Louisiana, the Aransas River in Texas, and even as far north as the South Fork Licking River in Ohio. To fully grasp the gravity of this event, it is crucial to understand the severity of the drought that set the stage. The data from the U.S. Drought Monitor on May 19th and 20th paints a stark picture. An astonishing 99% of the southeast region was officially in drought, with 62% experiencing either D3 extreme or D4 exceptional conditions, the two worst categories on the 5-step scale. State-level figures were just as dire. Arkansas was 99.5% in drought. Mississippi was at 93%. And Louisiana at 77%. As of March 31st, Georgia was 96% in drought, prompting the state to declare a Level 1 drought response on April 27th. Now, Florida sits under what the Miami Forecast Office has described as a transition to a significantly more wet weather pattern that is expected to last through the weekend and possibly into early next week. For the agricultural sector, this deluge is a double-edged sword, bringing both relief and risk. On the one hand, the news is unambiguously good for many. Row crops across the parched southeast, which have struggled to germinate, are about to receive a desperately needed soaking. Pastures and rangelands are set to begin greening up, offering hope for cattle producers. This is especially critical, given that the USDA has reported 61% of U.S. cattle production areas are in drought, a sharp increase from 31% the previous year. On the other hand, there is a significant downside. For winter wheat in the southern plains and mid-south, which is already nearing harvest, this late-stage rain could cause substantial damage and reduce the quality of the crop. It is a complex situation where the same water brings both salvation and destruction. The outlook for US winter wheat already presents a complex picture, with a good to excellent rating at a record low of just 30% and acreage planted for 2026 being the smallest since 1919, the agricultural sector is in a precarious state. A significant late-season rainfall event carries a dual potential. For some, it will be a saving grace, arriving on parched fields to rescue a struggling crop. For others, this same rain will fall upon mature, harvest-ready fields, where it can degrade both the test weight and protein content of the grain. While the net effect is likely to be positive, with the breaking of the drought being more valuable than the localized harvest disruptions, it's a powerful reminder that even desperately needed rain is not purely good news. This complexity extends to another pressing issue: wildfires. For 181 consecutive days, the US Drought Monitor map and the fire weather map have been functionally identical. By mid to late April 2026, a staggering 1.7 million acres had already burned, a figure double the 10-year average for that period. In Nebraska, the Merrill Fire alone consumed 640,000 acres, marking it as the largest single fire in the state's history. The drought had primed the continent, turning vast landscapes into a veritable tinderbox awaiting a spark. However, this incoming surge of moisture brings with it a significant and unambiguous benefit. Across the southeastern Gulf Coast, the rain is expected to dramatically raise the live fuel moisture content, pushing it back toward the normal range of 80 to 100%. This change is critical, as it effectively suppresses the conditions that allow fires to ignite and spread. It is a moment of welcome relief for a region on edge. In contrast, the fire weather forecast for the western half of the country remains unchanged, as it sits under a different segment of the same vast upper-level atmospheric pattern. But for the southeast, where the fire risk has been steadily building all spring on the back of a 1.31-year precipitation deficit, this rain will cause that danger to recede. This positive outcome is one of the clearest in a very complex forecast. To fully grasp the implications of this event, it is crucial to understand what meteorologists mean when they use the term saturated soils. This phrase appears frequently in official discussions from the National Weather Service, and it carries a specific operational meaning with profound physical consequences. When a forecast office, such as the one in Wilmington, Ohio, notes that saturated soils from previous rainfall will elevate the concern, they are communicating a precise condition. It means that a prior precipitation event has already filled the upper soil column to its field capacity. The tiny pore spaces between soil particles are now largely occupied by water, leaving no room for additional rainfall to infiltrate. Any new precipitation has nowhere to go but down to the next layer, or, more commonly, across the surface as runoff. In this state, a saturated soil behaves hydrologically, much like a paved surface, where the runoff coefficient approaches 1, meaning nearly all the rain that falls becomes immediate runoff into the local drainage network. This atmospheric river of moisture is now set to encounter two fundamentally different hydrological states on the ground, which will trigger varied responses. Across the Gulf Coast and the southeast, drought-baked soils have not experienced a significant soaking event for months. In stark contrast, the soils of the Ohio Valley have received repeated rainfall over the past 2 weeks and are already sitting near their field capacity. The resulting flash flood response will therefore vary by region. In the Ohio Valley, the effect will be a rapid rise in water levels on these saturated antecedent conditions. This is the kind of response that produces the flash flood warnings seen in Ohio's Fairfield, Franklin, and Licking counties, where 2 to 3.5 inches of rain have already fallen on wet ground. In the deep south, the response will be a rapid rise on hydrophobic, crusted antecedent conditions, where the rain hits a hardened surface and runs sideways. before it has a chance to soak in. Both of these scenarios produce dangerous flash flooding, but they do so through entirely different physical mechanisms, both of which the Weather Prediction Center has flagged in its morning outlook. Beyond the immediate flooding, the more subtle and perhaps more important story is what happens after the rain stops. In a normally hydrated environment, soil will slowly drain downward under the force of gravity, a process that recharges the shallow groundwater system over the following days and weeks. This infiltration is vital. However, for a drought-baked soil, even one that receives several inches of rain, this critical recharge may not occur if the precipitation runs off faster than it can be absorbed. The long-term recovery that the Southeast so desperately needs for the wells in rural counties, for the shallow surface water systems, and for the smaller agricultural reservoirs is entirely dependent on infiltration, not on runoff. The dramatic flood stage rises on major rivers, and the striking images of swollen creeks are the visible parts of this event, but they don't tell the whole story. The hidden part of this narrative is what will ultimately determine whether the drought relief is durable or merely transient. That question hinges on whether the water actually makes it into the ground. The answer is incredibly complex, depending on the rate of precipitation, the antecedent soil condition, the slope of the terrain, the type of ground cover, and a half-dozen other variables that change from one subregion to the next. Consequently, the Southeast is expected to see a heterogeneous response. Some of this rainfall will do exactly what the drought maps need it to do, replenishing the parched earth. But some of it will simply wash off the surface, producing floods without meaningful groundwater recharge. The true outcome of this event will not be visible in the immediate satellite imagery, but will instead reveal itself slowly in the U.S. Drought Monitor updates over the next 4 to 6 weeks. So, what is this vast atmospheric system truly carrying? It is a vessel of contradictions. It holds drought-busting rain for the Southeast, the Gulf Coast, and the Ohio Valley. Simultaneously, it brings a severe flash flood risk to these same drought-primed regions. For agriculture, it promises a net positive impact, albeit with some disruptive harvest-side noise. It delivers fire weather relief for the Southeast, yet leaves the fire threat in the West completely unchanged. It is a powerful illustration of the intricate and often conflicting nature of our planet's weather systems. And beneath all of this, another potential is stirring. The very source of this moisture, sitting in the lower troposphere over the Western Caribbean, is being shaped by a lifting trough, bounded by the Bermuda High and fueled by the heat reservoir of the sea surface. These are the classic conditions that can lead to tropical cyclogenesis. As this enormous body of moisture drifts, just 4 days from the official opening of hurricane season, the world's weather models are beginning to ask a different question. The concern is no longer just whether it will rain in Tallahassee on Saturday, but whether this entire body of moisture will organize itself into something with a name. That question is where our journey takes us next. Before we turn our attention from the cure to the potential threat, it is vital to grasp one central idea. The life-giving rain that is now arriving on shore is born from the very same atmospheric conditions that can spawn hurricanes. These are not two distinct meteorological stories unfolding in parallel. They are, in fact, two possible outcomes originating from a single, complex setup. This atmospheric duality is at the heart of our story, a reminder that, in nature, relief and risk can often be intertwined. This brings us to the core thread of our narrative, a concept that every following detail will circle back to. The vast air mass currently breaking the most severe drought in modern records is the exact same air mass that the world's major weather models are scrutinizing for tropical development. The arrival of drought relief and the potential for the season's first storm are not separate phenomena driven by different atmospheric forces. Instead, they represent two expressions of the same upper-level configuration. The cure is delivered on the same current of air that carries the threat. The region cannot receive one without also being exposed to the other. Understanding why this is mechanistically true is crucial, as it is not an editorial claim to be taken on faith, but a physical reality. The mechanism begins with a deep upper-level trough that has been digging into the Bay of Campeche over the last 48 hours. This feature is performing two critical jobs at once. Its first function, the one bringing welcome relief, is to lift immense tropical moisture from the Western Caribbean, pumping it northward across the Gulf Coast and into the southeastern United States. This is the source of the drought-breaking rain, yet, at the same time, this trough is performing a second task. It is providing the essential upper-level dynamical support that early-season tropical cyclones require in order to organize. For a closed, low-pressure system at the surface to intensify, it needs what is known as upper-level divergence, air moving away from its center at high altitudes. This process essentially ventilates the system, allowing the surface circulation to deepen and permitting convection to consolidate into organized bands instead of dissipating. The very trough that is lifting moisture northward to fall as rain over Pensacola is, on its eastern flank, producing the precise pattern of upper-level divergence that any forming surface circulation would need to feed upon. The trough's work is not finished when it delivers rain. It is simultaneously creating an enabling environment for cyclogenesis, the birth of a cyclone in the Western Caribbean, should a surface low manage to organize beneath it. This single atmospheric feature, therefore, carries with it both a blessing and a latent danger. The other half of this powerful atmospheric engine is the Bermuda High. Currently, this sprawling area of high pressure is situated over the southwest Atlantic. Along its western flank, it is actively pumping warm, humid air northward. This is the pathway that draws moisture from the Caribbean, across Cuba and the Gulf, and up into Florida and Georgia, feeding the rain system. But the Bermuda High also dictates the steering currents for any tropical system that might form. With the high positioned where it is now, a tropical system organizing in the Western Caribbean or the Bay of Campeche over the next 1 to 2 weeks would be steered northward, directly into the Gulf of Mexico. This alignment creates a stark geometric reality for the coming weeks. The configuration that makes the breaking of the drought possible is the same configuration that, if a storm were to form, would drive it toward the Gulf Coast. It would guide it into the very same landscape that is, by then, only partially recovered from 181 days of dryness. The trough that brings the rain is the same trough that gives a storm a place to organize. The high that lifts the moisture is the same high that would steer a storm into the Gulf. Relief from the drought and the formation of a tropical cyclone are not two different scenarios. They are the same scenario, separated only by a single variable. Whether a closed surface low can successfully consolidate within the vast moisture envelope that the trough and the high are already painting across the map. And that brings us to the question being posed to every major weather model in the world right now. The question is not whether there will be rain on the Gulf Coast. That has already been answered. The rain is here. The critical question is whether, at some point between June 1st and June 10th, a closed surface low will manage to consolidate inside this moisture-rich environment. This is the point of uncertainty that scientists are now watching with intense focus. We are entering a calendar window that has a colloquial name in the meteorological community: early season tropical shenanigans. This is a term of art used by broadcast meteorologists to describe the period from late May through the first 10 days of June. It is a time when the conditions favorable for tropical development in the Caribbean and Gulf are often present, even though the overall climatological probability of a storm remains low. It is a period defined by potential, where the atmosphere shows its capacity for surprises. History tells us that this potential is real. About a third of all Atlantic hurricane seasons produce a named storm before June 15th, and roughly 1 in 8 produces one before the official start date of June 1st. Of the named storms that do form in late May or the first half of June, the vast majority originate in one of 3 specific geographies: the Western Caribbean Sea, the Bay of Campeche, or the Eastern Gulf of Mexico. These locations are consistent breeding grounds for a reason. They are where several key ingredients reliably come together. They consistently combine warm sea surface temperatures with the kind of upper-level divergence that early season troughs provide. They are also where the Madden-Julian Oscillation, the single largest source of weather variability within a tropical season, often parks its convectively active phase during late May and early June. Finally, these regions are where the climatological minimum for vertical wind shear sits in the late spring, before the Bermuda High strengthens and the upper-level subtropical jet retreats toward the pole. Right now, all 3 of those conditions are falling into place. Sea surface temperatures in the Western Caribbean and Bay of Campeche are running warm. The Madden-Julian Oscillation is forecast to be in phases 1, 2, or 8, its convectively active phases for the Western Hemisphere, through the entire June 1st to 10th window. Furthermore, Atlantic vertical wind shear is forecast to weaken, and the trough we just discussed is providing that crucial upper-level divergence right where a surface low would need it most. This is precisely what the ensemble models are seeing. They are not inventing a scenario out of thin air. They are observing the convergence of every major variable that contributes to tropical cyclogenesis, all aligning at the same time, in the same place, and during the same calendar window. The ensembles are therefore responding exactly as they should, by showing a non-zero probability of development within that window. It is a logical, data-driven conclusion. So, before we proceed to the noise and speculation that often surrounds these events, it is important to plant a flag here, to remember what is fundamentally true while the louder versions of the story unfold. The core truth is this: the drought is breaking. The atmosphere is, at this moment, delivering profound and necessary relief. The very atmospheric conditions that promise to deliver much-needed relief are, in a profound paradox, the same conditions that could give rise to a tropical storm. With the official start of hurricane season just 4 days from this documentary's release, this convergence takes on a particular weight. 3 independent ensemble forecasting systems all point to the same window of time and the same air mass for potential development. It is this confluence of factors that makes this discussion so necessary. The narrative of a storm named Arthur forming immediately is not just premature, it overlooks the more nuanced, legitimate forecast. The real story is the possibility of development within the very air mass that is breaking the drought, but in a time frame that begins in 4 days. This reveals a dual error in the prevailing online hype, one of timing and another of interpretation. To understand this, we must first examine the story of the storm that isn't actually forming. Over the last 48 hours, anyone with an interest in weather has likely encountered the sensational thumbnails online. A vibrant, swirling vortex of red and orange over the Caribbean, accompanied by the name Arthur in bold lettering. Headlines suggest a system that is developing fast, forming now, or is in some way imminent. The clear implication is that the first named storm of the 2026 Atlantic hurricane season is not just on its way, but is already here in all but name. This messaging is designed to create a sense of urgency, suggesting that a significant threat is materializing by the end of the week. But does this dramatic portrayal align with the scientific reality? For a grounded perspective, we turn to the official position of the National Hurricane Center. Before any other analysis, their statement provides the essential facts. In the Atlantic Tropical Weather Outlook issued at 8:00 a.m. Eastern Daylight Time, on the 27th of May, 2026, forecaster Berg in Miami offered a clear and concise assessment. The report stated that for the North Atlantic, the Caribbean Sea, and the Gulf of Mexico, no tropical cyclone formation was expected over the next 7 days. This was the entirety of the outlook. There was no invest area, no designated region of interest, and no colored circles yellow, orange, or red on their maps. The probability was 0 through the following Tuesday. In a parallel report for the Eastern Pacific, forecaster Reinhardt from the same office issued an identical forecast. No tropical cyclone development anticipated for the next 7 days. This raises a critical question. If the official expert consensus is so clear, why are social media feeds saturated with images of an impending storm, Arthur? The answer lies in understanding what separates the dramatic imagery used in these thumbnails from the strict meteorological criteria that define a tropical storm. Once this distinction is clear, the power of such hype begins to fade. The next time you encounter one of these images, and you likely will many times over the coming week, you will be equipped to discern whether it represents a genuine signal or is merely atmospheric noise, without needing an external voice to tell you. A true tropical storm is a meteorological entity defined by 4 specific and non-negotiable properties. The first of these is a closed surface circulation. This means there must be a low-pressure center that can be clearly identified at the Earth's surface, with winds rotating around it in a complete, closed loop. This is not a simple chevron shape, a comma cloud, or a line of thunderstorms moving from west to east. It is a distinct, continuous rotation. Meteorologists can identify this feature using surface observations from buoys and ships, by observing the curvature of low-level clouds in satellite imagery, and with scatterometer data from instruments that measure wind speed and direction over the ocean. Without a closed surface circulation, there can be no tropical cyclone. This is the absolute starting point. The second essential characteristic is a warm core thermal structure. At their heart, tropical cyclones are fundamentally different from the low-pressure systems common in the mid-latitudes. The air at the center of a tropical system, at the altitudes where it is most organized, is warmer than the surrounding air at the same height. This is what distinguishes it from an extratropical low, which possesses a cold core. This warm core signature is the engine of the storm, and it can be detected using satellite-derived temperature soundings and data from aircraft reconnaissance when missions are flown. A system's response to environmental winds also offers clues to its thermal structure. If a system lacks a warm core, it is not a tropical cyclone. It might be a low-pressure area, an organized convective vortex, or a tropical disturbance, but it cannot be classified as a tropical storm. Third, a developing storm must exhibit organized convective banding around its low-pressure center. True tropical cyclones develop distinctive spiral bands of deep convection powerful thunderstorms that rotate around the central point. These bands possess a clear structure that is visible on satellite imagery. They are not simply a disorganized blob of thunderstorms moving in a single direction. Instead, they are highly organized features with identifiable inflow regions where air is drawn in, outflow regions where air is expelled at the top, and often a developing eyewall structure near the system's core. A chaotic pile of thunderstorms without this coherent organization is not a tropical cyclone. Finally, there is the official procedural step, an active invest area designation from the National Hurricane Center. The NHC employs a numerical system using labels like Invest 90L to identify areas of interest that meteorologists are actively monitoring for potential development into a named storm. When a disturbance is elevated to invest status, it triggers a series of formal actions. The NHC begins running dedicated numerical models for it, issues more frequent public updates, and starts coordinating with the Air Force Reserve hurricane hunters for possible reconnaissance flights. As of the morning of May 27th, there were 0 invest areas in the Atlantic Basin, the Eastern Pacific, the Caribbean Sea, or the Gulf of Mexico. no system was being officially tracked for development. So, what are the hype-driven thumbnails actually showing? The imagery being used is a satellite loop of the deep tropical moisture surge that has been the focus of our discussion, the very same atmospheric feature that is bringing an end to the drought. On a visible spectrum satellite loop, this vast body of moisture does indeed look dramatic and powerful. However, it is simply a large, moisture-rich air mass. It lacks the closed circulation, the warm core, and the organized spiral banding required to be classified as a developing tropical cyclone. The image captures a real phenomenon, but the interpretation attached to it is fundamentally incorrect. A vast plume of moisture, the deepest pool to lift out of the Caribbean this year, is currently making its way northward. As this air mass rises through the boundary layer, it builds tall convective towers, generates flashes of lightning, and produces bands of heavy rain. To an untrained eye, the satellite imagery bears all the hallmarks of a developing tropical system. This visual ambiguity is precisely what some channels exploit. By overlaying this imagery with the name Arthur in bold red letters alongside a dramatic arrow, they can create a compelling illusion. The average viewer cannot easily distinguish between a genuine closed circulation and a simple moisture surge. The result is a successful transaction for them. They secure the click, the watch time, and the subsequent ad revenue. But a closer look at the meteorological data reveals a different story. The imagery shows no closed surface circulation, no warm core thermal structure, and no organized convective banding. What we are witnessing is simply a powerful band of thunderstorms moving in sync with the upper level flow, with no associated invest area. This distinction is critical, as it separates a scientific reality from a carefully constructed narrative. It is worth taking a moment to understand the economics driving this, because it speaks to a larger issue of information integrity. The business model of these hype-focused outlets is built upon the wide gap that exists between what appears scary on a satellite loop and what is actually threatening in meteorological reality. The video that earns the most engagement is often the one that most effectively exploits this gap. The true cost to the viewer is not the click itself, but the gradual erosion of trust. After being exposed to enough false alarms, people may either stop trusting any weather coverage, become desensitized to legitimate warnings when they are issued, or develop a persistent anxiety about events that never materialize. None of these outcomes are beneficial for the communities who genuinely rely on precise weather information when a real storm does form. This hype is not without consequence. It carries a downstream cost, and that cost is paid by the people living along the Gulf Coast, who need clear, accurate hurricane guidance when an actual threat appears on the horizon. Our position at Calm Space has always been to be the channel that helps you distinguish when the science is the story and when the noise is the story. Today, the noise has become so loud that it is now part of the story itself, primarily because it risks obscuring the actual signal that the real forecast ensembles are sending. And that authentic signal is where the truly interesting developments lie. This brings us to the crucial element that the hype-driven narratives are missing. While they are incorrect about a storm named Arthur forming today, they are also overlooking the part of the forecast that is genuinely worth discussing. A legitimate signal for potential development is indeed emerging, and it is being picked up by the European Centre for Medium-Range Weather Forecasts, the US Operational Ensemble, and even Google DeepMind's advanced AI weather model. This signal points to possible activity within the very same air mass we have been tracking, but in a window stretching from the 1st to the 10th of June. That is not now. It is next week and the week that follows. This is a real signal, and its significance is amplified by the fact that it is coming from 3 independent modeling systems, each with different physics and architectural foundations. In fact, It represents one of the more compelling tropical development signals to appear this late in May in recent years. The hype channels are therefore wrong on two fronts. First, they are wrong about the timing, claiming a storm is imminent when the models point to next week. Second, they are wrong about the meaning, treating it as a guaranteed Arthur, when the legitimate signal is for times possible, times development in a future window, not a certain storm in this moment. The viewer who watches their content is left with a forecast that is distorted in two directions at once. Here, we hope to provide the correct one. So, let's examine what the ensembles are actually saying. There are three major weather modeling systems whose ensemble forecasts are worth taking seriously when evaluating a potential tropical development window. The first is the Operational Ensemble from the European Centre for Medium-Range Weather Forecasts in Reading, England. The second is the Operational Ensemble produced by the US National Centers for Environmental Prediction in College Park, Maryland, known as the GEFS, or the Global Ensemble Forecast System. The third, a more recent addition to this landscape, is the ensemble generated by Google DeepMind, the AI weather modeling group at Google that utilizes their GenCast and GraphCast systems. Each of these three systems is built on different principles. They use different underlying physics, operate at different resolutions, employ different data assimilation methods, and follow different philosophies for generating their ensembles. In short, they are about as independent as three modern operational systems can be. This independence is key. When they disagree, it highlights meaningful uncertainty in the forecast. But when they agree, even on a low probability signal, that agreement itself becomes the signal. And right now, in their May 27th runs, they are all agreeing on a low probability signal for possible tropical development in the Western Caribbean or northeastern Gulf of Mexico, sometime between June 1st and June 10th. Let's walk through each one. First, the European Centre's operational ensemble runs 51 distinct members for each forecast cycle. Each member is initialized with slightly different starting conditions to capture the inherent uncertainty in the atmospheric analysis. As of the latest 12 UTC cycle, approximately 5 to 8 of those 51 members are forecasting a closed low-pressure system somewhere in the Western Caribbean Sea or the northeastern Gulf of Mexico during the June 1st through June 5th window. This equates to a probability of development in the range of 10 to 16%. While that is not a high-confidence forecast, it is a non-zero probability at a 10-day lead time, which is meteorologically meaningful. The European ensemble is generally regarded as the most skillful operational ensemble on the planet for medium-range tropical forecasting, consistently outperforming others on track and intensity guidance. When this model puts 5 to 8 members on a closed low 10 days out, it is a signal to pay attention. Next, we turn to the US Operational Ensemble, the GEFS, which runs 31 members. In the same window, it is showing a higher count of members forming a closed low. The exact number varies by cycle, but has been consistently in the range of 8 to 12 members out of 31. This suggests a higher probability of development, somewhere between 25 and 40%. Now, this is where a degree of scientific skepticism is required. The GFS, the deterministic model whose ensemble is the GEFS, has a well-documented historical bias toward being over-aggressive on early-season tropical cyclogenesis. The model has a known tendency to spin up closed surface circulations in environments where other models, like the European and UK versions, do not. Historically, these forecast circulations do not always verify in reality. Therefore, while the higher probability shown by the GEFS is consistent with the European signal, it must be interpreted with this important context in mind. While both the American GFS and the European Center models are observing the same favorable atmospheric conditions, their interpretations differ. The GFS model's output appears structurally inflated, whereas the European Centre's probability is likely a more accurate reflection of the true odds, which we can estimate at around 10 to 20%. However, a third system warrants our closest attention, as it represents a newer force in operational forecasting. This system is Google DeepMind's GenCast, a generative AI ensemble that produces 50 distinct forecast members each cycle. Its performance during the 2025 Atlantic hurricane season was remarkable, where it consistently outperformed traditional models in tracking tropical systems. The architecture of GenCast is fundamentally distinct from the European Centre's spectral model and the US GFS. It is a machine learning system trained on the vast ERA5 reanalysis dataset. Instead of relying on hand-coded numerical equations, it learns the underlying physics of the atmosphere through deep neural networks. This groundbreaking system, published in the journal Nature in late 2024, demonstrated its power during the 2025 Atlantic season. For tropical cyclones, its track forecasts at 5 to 10 day lead times were, on average, 12 to 15% more accurate than the European model, and 20 to 25% more accurate than the GFS. Currently, GenCast is indicating that approximately 3 of its 50 members are converging on a closed, low-pressure signature, either in the Western Caribbean or the northeastern Gulf of Mexico, within the window of June 1st to June 5th. This 3 out of 50 ratio translates to a 6% probability. While that may sound low, the true value of GenCast in this situation is not its absolute probability figure. The crucial insight is that an entirely different type of forecasting architecture, an AI model, is independently detecting the same potential signal in the same time frame as the traditional dynamical models. When a numerical model and a machine learning model concur on a low probability tropical development signal, it suggests something more significant than either model could indicate on its own. So, let us consider what this convergence truly represents. We have 3 independent operational ensembles: the European, the US, and DeepMind's GenCast. These systems are built on 3 entirely different architectures: a spectral numerical model, a semi-Lagrangian numerical model, and a generative AI. Furthermore, they originate from 3 different agencies and countries: the ECMWF in England, NCEP in the United States, and Google, a distinct institution also in the US. The remarkable fact is that all 3 are pointing toward the same low probability signal for development within the same 5-day window. The probability range across these systems spans from a conservative 6% to an aggressive 40%, with the most skillful system placing the odds between 10 and 16%. This is a genuine, non-trivial signal, especially at a lead time of 10 days. What broadcast coverage may not fully explain is the reason behind this consensus. The models are not converging simply by chance or by observing the same statistical noise. They are converging because they are all detecting the same fundamental physical conditions in the atmosphere. The primary driver is the Madden-Julian oscillation, or MJO, which is the single largest source of weather variability in the tropics on a sub-seasonal scale. This MJO is a vast, eastward propagating envelope of enhanced convection that circles the equator roughly every 40 to 60 days. Forecasts indicate that the MJO will be in its Western Hemisphere active phases, specifically phases 1, 2, and 8 on the standard scale throughout the entire period from June 1st to June 10th. When the MJO enters these phases, the entire tropical basin in the Western Hemisphere experiences conditions highly conducive to storm formation. These include enhanced upper-level divergence, which allows air to rise and vent away from a developing storm, reduced vertical wind shear, which prevents the storm from being torn apart, and increased low-level convergence, which draws moist air into the system's center. These three elements are the large-scale prerequisites for tropical cyclogenesis. The models are not inventing a storm out of thin air. They are predicting potential development in what is expected to be the most favorable sub-seasonal environment the Atlantic Basin will see in the coming month. Adding to the influence of the MJO, the Atlantic's vertical wind shear is also forecast to weaken across the Western Caribbean and the Gulf during this same window. Vertical wind shear, the change in wind speed and direction with height, is the principal adversary of a developing tropical cyclone. High shear can rip a nascent system apart before it has a chance to organize its structure. Conversely, low shear provides a calm environment, allowing the storm's warm core to consolidate and strengthen. The shear forecast for June 1st through the 10th is, depending on the model, projected to be anywhere from below average to well below the climatological norm, a condition that strongly favors development. The final piece of this puzzle is the ocean itself. Sea surface temperatures across the Western Caribbean and Gulf of Mexico are running warm. While the exact numbers vary by location and week, the basin is generally 1 to 1.5 degrees Celsius above the 1981 to 2010 climatological average for this time of year. This is not the extreme warmth of peak season, when surface waters can exceed 29 degrees Celsius, but it provides more than sufficient energy for the formation of a low-end tropical storm. To fully grasp the weight of these signals, a piece of context is essential. The European Center's ensemble is the same system that, during the 2017 Atlantic hurricane season, was already showing signatures of what would become Hurricane Harvey roughly 9 days before its formation, while US guidance was still uncertain. It was also the system that flagged Hurricane Sandy's eventual westward turn into the New Jersey coastline, 4 days before American operational models fully committed to that track. The European model has earned its stellar reputation through decades of verification studies. The mean absolute error on its 5-day tropical track forecasts is consistently in the 150 to 200 kilometer range, which is considered the operational gold standard. Therefore, when this highly skilled ensemble shows 5 to 8 of its members indicating a closed low in the Western Caribbean and Northeastern Gulf for the June 1st to 5th window, its history suggests that this signal should be treated as real, even at a 10-day lead time and with a low absolute probability. A low probability signal from a high-skill model is profoundly different from a similar signal from a low-skill one. We are looking at the former. The GFS model, by contrast, possesses known structural biases that meteorologists routinely adjust for. The model has a tendency to spin up closed circulations in the Western Caribbean during May and June at a rate that does not often verify in reality. Studies have shown that the false alarm rate for these early season cyclogenesis signals in the GFS is on the order of 50%. Consequently, when the GFS shows 12 of its members forecasting a closed low for early June, the operational interpretation is to effectively halve that probability. This adjusts the raw 25 to 40% chance down to a more realistic 12 to 20%. This adjusted figure aligns quite well with the more trustworthy probability from the European model. The convergence I described earlier is therefore rooted in a real, underlying physical signal, not merely the inflated expression of it from the GFS. The forecasting model known as GenCast warrants a closer look, as its architecture is fundamentally new and its implications are still being absorbed by the operational forecasting community. This system was introduced in a paper published in the journal Nature Times in late 2024 by Google DeepMind's Weather Group. The study demonstrated remarkable skill in medium-range predictions for tropical cyclones, outperforming the European Center's ensemble model by a significant 12 to 15%. GenCast is trained using the ERA5 reanalysis dataset, a comprehensive 4, 5, year record of the three-dimensional state of the atmosphere, which itself is reconstructed from observations via the European Centre's data assimilation system. From this vast historical record, the model learns the underlying physical dynamics of the atmosphere through a generative diffusion process. This approach raises a profound question. What does it mean for a machine to learn the weather rather than calculate it? Critically, the system makes no use of the hand-coded physics equations that are the bedrock of traditional numerical models, like the European model and the GFS. There are no parameterizations for moist convection, no schemes for radiation transfer, and no equations for atmospheric boundary layer mixing. Instead, the system learns atmospheric patterns directly from observed data and then reproduces them in its forecasts. The fact that an architecture so profoundly different from the European and GFS models is independently identifying the same potential signal between June 1st and 10th is deeply meaningful. It suggests that whatever atmospheric conditions are currently developing in the Western Caribbean and the Gulf of Mexico, they are recognizable to multiple, fundamentally distinct ways of interpreting the atmosphere. The signal gains credibility because three different mathematical systems have all reached a similar conclusion. That said, it is crucial to be careful about overinterpreting a 10% probability 10 days into the future. A 10% chance of development inherently means there is a 90% chance that no storm will form. The most likely outcome for the June 1st to 10th window is that nothing organizes. In this scenario, the surge of moisture simply passes through, delivering its rain across the southeast before dissipating, never consolidating into a closed circulation. That is the modal, or most probable, outcome. The 10 to 15% probability of development represents what is known as the tail of the distribution. It is a fat tail, meaning it is a more significant possibility than climatology alone would suggest, precisely because the underlying environmental conditions are favorable. But it is still the tail an unlikely, though not impossible, event. If development were to occur, it would most likely manifest as a low-end tropical storm. This is the kind of system that receives a name, persists for 2 or 3 days, and produces drought-busting heavy rainfall across the Gulf Coast and Florida. It would likely prompt local flood warnings, but not require any large-scale evacuations, generating a moderate level of excitement within the broadcast meteorology community for about 48 hours. Its characteristics would probably include maximum sustained winds between 40 and 60 miles per hour, with a central pressure in the high 900s to low 1000s in millibars. The storm's track would be uncertain, but could take it anywhere from the eastern Yucatan Peninsula northeastward into the eastern or central Gulf, with a potential landfall in Florida, or even a recurvature through the Western Caribbean and back into the Atlantic. The probability of a major hurricane forming in this window is effectively 0, and the chance of a Category 1 or 2 hurricane impacting the U.S. Gulf Coast is likely under 5%. The most probable result of a successful cyclogenesis would be a tropical storm that meteorologists in Tampa and Pensacola feature in their newscasts for a few nights, delivering beneficial rain to a parched Florida and South Georgia, and then dissipating before its name is widely remembered. If it does form, it will likely be named Arthur, the real Arthur, not a phantom storm promoted by hype channels. But this potential storm itself is not the true story. The real narrative lies in what this first storm of the season represents in a much larger context. To understand that, we must turn our attention thousands of miles away to what is happening in the equatorial Pacific Ocean. This is a story unfolding in a different ocean basin, on a different timeline, and driven by a different mechanism, yet it feeds directly into the Atlantic hurricane season we are about to enter. Part 6. The ENSO Handoff. Let us examine the data for the Oceanic Niño Index, or ONI, over the past 6 seasons. The ONI is the 3-month running average of sea surface temperature anomalies in the Niño 3.4 region of the equatorial Pacific Ocean. This critical area is located in the central Pacific, between 5 degrees north and 5 degrees south latitude, and stretching from 170 degrees west to 120 degrees west longitude. It serves as the standard metric used by the National Oceanic and Atmospheric Administration's Climate Prediction Center to classify the state of the El Niño Southern Oscillation. When the ONI is at or below minus 0.5 degrees Celsius for 5 consecutive overlapping 3-month periods, we are in a La Niña. Conversely, when the index is at or above plus 0.5 degrees Celsius for 5 consecutive seasons, we are in an El Niño. Any value in between is considered neutral. The recent values tell a clear story of transition. For September, October, November 2025, the index was negative 0.51, a La Niña state. It remained there for October, November, December 2025 at negative 0.55, and November, December, January 2026 at negative 0.54, but then a shift began. For December, January, February 2026, the value rose to negative 0.37, a cold side neutral. By January, February, March 2026, it was negative 0.15, much closer to the middle. Finally, for February, March, April 2026, the index crossed into positive territory at plus 0.11, a warm side neutral. This represents a remarkable swing of plus 0.66 degrees Celsius in just 3 overlapping seasons, a trend that the NOAA data explicitly labels as warming. The sea surface temperatures in the Niño 3.4 region rose from 25.97 degrees Celsius in the November to January period to 27.28 degrees in the February to April period. The atmospheric machinery that responds to these ocean temperatures is now beginning to feel that warmth. As a result, the Climate Prediction Center has an El Niño watch in effect. The 5-day update from the previous forecast cycle placed the probability of El Niño onset at 82 to 98% during the May, June, July window. That is now a near certainty, with a 96% chance of persistence into the winter of 2026 to 2027. Furthermore, there is roughly a 1 in 3 probability of this event reaching strong or very strong intensity, defined as a peak anomaly of plus 1.5 or plus 2 degrees Celsius by the December, January, February timeframe. The physical reservoir for this basin-scale warming is found not at the surface, but deep in the ocean. In a previous Calm Space segment on the Pacific heat wave, we explored the subsurface Kelvin wave that has been propagating eastward across the equatorial Pacific for the past several months. This wave is characterized by astounding temperature anomalies of plus 6 to 7 degrees Celsius at a depth of 100 meters. This vast reservoir of subsurface heat provides the inertia behind the warming surface anomaly. The process creates a powerful feedback loop. The surface will continue to warm as this deep water continues to upwell, and that upwelling will persist as long as the trade winds remain relaxed. This is the engine driving the impending El Niño. So, what does this powerful shift unfolding in a distant ocean mean for the Atlantic hurricane season? In the vast and intricate world of tropical meteorology, few connections are as well established as the link between El Niño and hurricane activity in the Atlantic. This relationship is a classic example of a large-scale teleconnection, where events in one part of the world profoundly influence the weather thousands of miles away. When an El Niño is underway, the unusually warm waters of the central Pacific Ocean fuel powerful convection. This process invigorates the upward motion of the Walker circulation over the Pacific, which in turn strengthens its downward, sinking branch over the tropical Atlantic. The consequence for the Atlantic is a significant increase in vertical wind shear, a change in wind speed and direction with height. Specifically, this manifests as stronger westerly winds in the upper atmosphere and weaker easterly trade winds near the surface. This shearing environment is hostile to tropical cyclones, effectively tearing them apart before they can organize and intensify. This atmospheric tug-of-war raises a critical question. Is this suppression effect immediate, or is there a delay? The data shows that the Atlantic basin is most reliably quieter during El Niño years, in the peak window of August, September, and October, when the majority of storms typically form. However, the relationship is neither absolute nor instantaneous. In the early part of the season, from May through the first half of July, the suppressive influence of El Niño has often not yet fully taken hold, as the atmosphere requires time to adjust to the changes in the equatorial Pacific. This time lag creates a fascinating dynamic. During the early season, the environment for storm formation can remain quite favorable, even as the Pacific is warming. This is particularly true in years when the Atlantic basin itself begins the season with its own anomalously warm sea surface temperatures. The warm local conditions in the Caribbean and the Gulf of Mexico can act as a powerful engine for development, overpowering the still developing basin-wide suppression from El Niño. This is precisely the scenario unfolding at present. The Atlantic basin is currently marked by exceptionally warm waters across the Caribbean and the Gulf. Furthermore, the Madden-Julian Oscillation, a major fluctuation in tropical weather, is in a phase that encourages storm formation. Forecasts for the period of June 1st through June 10th even suggest that vertical wind shear will weaken. So, while the equatorial Pacific is indeed warming, it has not yet reached the critical threshold where its shear-inducing effects are felt across the Atlantic. This leaves a wide-open window for early-season tropical activity to emerge in the Western Caribbean and the Gulf of Mexico. To understand the potential outcomes of this complex setup, we can turn to historical analogues. It is vital to approach these comparisons with caution. They serve as valuable references for scale and pattern, but should never be mistaken for direct predictions. The first and most dramatic analogue is the hurricane season of 1933. Occurring before the satellite era began in 1966, this season was the second most active on record, according to modern reconstructions, producing an astonishing 20 named storms, 5 of which became major hurricanes. Remarkably, this intensely active season unfolded against the backdrop of a transition toward El Niño and a record warm Atlantic Ocean. The basin's exceptional warmth fueled sustained storm development throughout the entire season. The suppressive effects of El Niño did not fully materialize until late in the year, by which point the basin had already generated the vast majority of its storms. While the 1933 season provides a compelling historical parallel, it is not a perfect mirror for the year 2026. The Atlantic in 2026 is not as profoundly warm as it was in 1933. The pacing of the El Niño Southern Oscillation, ENSO transition, is different, and the overall climate baseline has shifted over the intervening decades. Yet, the structural lesson from 1933 remains profoundly relevant. A hurricane season can become extremely active during an El Niño transition if the basin begins with its own significant warm anomalies. This history suggests that the most active part of such a season tends to be the early to middle months, before the suppressive wind shear from El Niño becomes the dominant force. This historical parallel offers a valuable lesson, not as a forecast, but as a reminder of nature's complex interplay of forces. Let's delve a little deeper into the 1933 analog, as it represents the closest historical match for the early season conditions of 2026. Understanding it helps illustrate both the utility and the inherent dangers of using such comparisons. In 1933, The equatorial Pacific was just emerging from a La Niña phase and was slowly shifting toward weak El Niño conditions during the spring and early summer. Simultaneously, sea surface temperatures across the Atlantic basin, especially in the Caribbean and tropical Atlantic, were anomalously high, the warmest on record based on available historical data. This potent combination of a warm Atlantic and a transitioning ENSO state produced one of the most active early and middle hurricane seasons in the modern record. As noted, modern reconstructions count 20 named storms, with 5 achieving major hurricane status of Category 3 or higher on the Saffir-Simpson scale. The season began early, with the 1933 Trinidad hurricane forming in May and strengthening to a hurricane by mid-June. The season's peak activity occurred in September and October, with several major hurricanes making landfall in the United States and the Caribbean. Of course, we must apply appropriate caveats to this 9-3-year-old reconstruction. The quality of the data is not comparable to what we have today. The era of satellite monitoring did not begin until the mid-1960s, and routine aircraft reconnaissance only started in the late 1940s. Consequently, some storms in the 1933 record were identified solely from ship reports and coastal observations. This means that their true peak intensities and exact track positions carry a degree of uncertainty. The true value of this analog, therefore, is not in the precise numbers, but in the structural lesson it provides. It demonstrates that a basin with unusually warm sea surface temperatures during an ENSO transition window can spawn an exceptionally active season. The favorable local conditions in the Caribbean and Gulf can drive storm formation or cyclogenesis, even as the larger scale ENSO state is shifting. The great uncertainty is whether 2026 will follow a similar pattern, or if the ENSO transition will proceed quickly enough to suppress activity by mid-season, a question that current models are still debating. A second, more recent analog also offers valuable insight: the 2013 season. That year produced 14 named storms, a figure above the long-term average. This occurred despite the development of borderline El Niño conditions during the latter half of the season. The key feature of 2013 was that its activity was heavily front-loaded, concentrated in the early and middle months. The Caribbean and the Gulf of Mexico were responsible for most of the season's tropical storms, while late-season activity in the central and eastern Atlantic was stifled by the increased wind shear from the developing El Niño. In many ways, 2013 serves as a better modern template for what 2026 might become, a season defined by early activity in the Caribbean and Gulf before the large-scale shear pattern takes control. But this brings us to the element that remains genuinely unknowable in late May: the precise timing and intensity of the 2026 El Niño transition. The forecast models show a wide spread of possibilities, highlighting the inherent uncertainty. If the equatorial Pacific warms rapidly, reaching an anomaly of +1 degree Celsius or warmer by August, then the suppressive wind shear will likely kick in by mid-season. This would lead to suppressed activity across the Atlantic basin during the critical peak months of August, September, and October. Conversely, if the transition stalls, remaining in the neutral to weak El Niño range through those peak months, the outcome could be very different. In that scenario, the Atlantic basin would retain its anomalously warm sea surface temperatures without the counteracting effect of wind shear, potentially allowing the season to produce activity well above the long-term average. This is the central drama that will define the months ahead. As the calendar turns towards summer, a fundamental uncertainty hangs over the 2026 hurricane season. Forecast models for the August peak, based on the Oceanic Niño Index, present a wide spectrum of possibilities, with projections ranging from a modest +0.5 degrees to a much more active +1.8 degrees. From the vantage point of late May, The true nature of the season remains unknowable. We can only learn which path we are on when the season itself begins to reveal its character. This is where the moisture surge we have been tracking becomes so critical. The period from June 1st to June 10th acts as the season's first true test, offering a glimpse into which scenario is unfolding. If a named storm were to form within this window, an outcome ensembles currently place at a 10 to 20% probability, it would suggest the front-loaded, more active scenario is materializing. Conversely, if this period passes without any tropical development, it does not guarantee a quiet season, but it would be the first piece of evidence aligning with a suppressed activity model. In essence, the next 2 weeks will provide the first concrete data point on the personality of the 2026 season. What makes this moment so compelling is that the very moisture breaking a widespread drought is the same body of air that could fuel the season's first storm. Should a tropical system organize, it will do so within the exact air mass currently bringing desperately needed rain to the Gulf Coast and Florida. These are not two separate atmospheric stories unfolding in sequence. They are two potential outcomes of a single, vast, upper-level configuration. The cure for the drought and the season's first threat are born from the same air. For 181 days, the country has awaited this relief, and it is now arriving on the very same atmospheric currents that, in just a few days, could begin to assemble into a formidable threat. The atmosphere does not offer a choice between these outcomes. It delivers both possibilities intertwined. We will revisit the profound implications of this duality later, but first, we must understand the engine driving it. To truly grasp the significance of this moisture surge, we must look beyond the rain and examine the vast atmospheric pattern that is producing it. This upper-level configuration is not a localized event. It is orchestrating several distinct weather phenomena simultaneously across the entire country. By studying these other effects, we can gain insight into the pattern's overall strength and persistence. This, in turn, helps answer a crucial question. Is this moisture surge a fleeting, one-week event? Or is it the beginning of a stable setup that could define the weather for the next month? To find the answer, we must zoom out and look at the rest of the map. There is a meteorological term that, once learned, you will begin to recognize everywhere in weather patterns: the omega block. This phenomenon describes a specific arrangement of the jet stream, where its flow contorts into the shape of the Greek letter omega. The pattern is characterized by a stationary, high-pressure ridge situated in the middle, flanked on either side by two cut-off or nearly cut-off low-pressure systems. When you see an omega block on a 500 millibar height map, you are witnessing a segment of the jet stream that has ceased its typical eastward progression. It has become locked into a stable configuration that can persist for a week or even longer, sometimes stretching to 10 days or 2 weeks. The high-pressure ridge in the center anchors warm, dry, and stable air over the land beneath it. Meanwhile, the lows on its flanks bring cool and unsettled weather to their respective regions. Once this block is established, the weather underneath it changes very little until the entire pattern finally breaks down. On the morning of the 27th of May, 2026, the reality of this pattern became undeniable as 4 separate National Weather Service offices in Philadelphia, Denver, Chicago, and Los Angeles all independently described the same blocking configuration in their morning forecast discussions. The Mount Holly office, serving New Jersey and eastern Pennsylvania, noted that an omega block setting up over the central United States would bring high pressure and dry conditions through at least Sunday. Far to the west, the Boulder office, covering eastern Colorado, identified a blocking upper-level high over the northern plains. In the Midwest, the Chicago office described an expansive area of surface high pressure linked to high-amplitude ridging that extended deep into Canada. Perhaps most strikingly, the Oxnard office for Southern California characterized an upper-low spinning over the Sacramento area as unusual for this time of year, producing weather more akin to that of Portland. That same office noted that on the back end of the block, heights would rise dramatically, from a January-like reading to 574 decameters by Friday. When four distinct offices used such similar language to describe the same continental pattern on the same day, it confirms the Omega block is not just a forecast model artifact. It is real, and it was already producing four simultaneous, large-scale effects across the country. The first of these effects was a distinct cooling trend east of the Mississippi River. The Omega block's eastern flanking low-pressure system settled over eastern Canada and the northeastern United States. Beneath this area of low pressure, temperatures began to fall below the seasonal average. On the 1st of June, Pittsburgh was forecast to see a high near 73 degrees Fahrenheit, with Detroit reaching only 75. Even Orlando, while not directly under the cutoff low, felt its influence through trough-induced cloud cover and rainfall, with temperatures dipping back into the mid-80s, which is cooler than normal for late May. The Boston NWS office wrote that temperatures would trend cooler late in the week, while the New York office noted a return to more normal temperatures for the period. Across the entire Northeast and Mid-Atlantic, the first days of June were poised to feel less like the start of summer and more like a return to late April, not cold or catastrophic, but a noticeable departure from the calendar. In stark contrast to the cool conditions in the east, the second major effect of the Omega block was unfolding over the northern plains and upper Midwest. Here, beneath the powerful high-pressure ridge at the center of the Omega, the air was subsiding. This sinking air compresses as it descends, and through the simple laws of physics, compressing air warms up. This process, combined with the strong solar heating of late May at high latitudes, where daylight approaches 18 hours, created the conditions for a significant heat event. The result was temperatures soaring well above normal, challenging records across the region. This dramatic tale of two climates, cool and unsettled in the east, hot and dry in the central plains, was not a coincidence. It was the surface signature of a single, unified, and powerful weather pattern locked in place over the continent. In their morning discussion, forecasters at the Weather Prediction Center highlighted an area of intense heat developing across the northern plains and upper Midwest. Widespread high temperatures were expected to climb into the 80s and 90s, with some parts of eastern Montana and western North Dakota potentially approaching or even surpassing 100 degrees Fahrenheit. This remarkable warmth is more than just a summer preview. It's a powerful signal of a much larger atmospheric event. For perspective, International Falls, Minnesota, right on the Canadian border, typically sees late May highs in the mid-60s, but was forecast to near 90 degrees by early June. Further south, Tucson, Arizona, could see record-breaking heat on Tuesday, June 2nd. The National Weather Service's experimental heat risk forecast, designed to communicate health risks, indicated widespread, moderate to major levels of concern through the week's end. In some areas, this represented a staggering temperature gradient anomaly of 120 degrees Fahrenheit. A 100-degree day in eastern Montana, where the average late May high for nearby Bismarck is 73 degrees, constitutes a +2.5-degree anomaly, an unusual level of heat for any month, let alone the first week of meteorological summer. Yet, on the other side of this atmospheric divide, a completely different story was unfolding. The third major effect of the weather pattern was a chill in the southwest, reminiscent of January. An upper-level low, part of the larger Omega block, had become cut off and settled over central California and the Great Basin, anchored near the Sacramento area at 555 decameters. Beneath this low, a cold air mass enveloped California, Nevada, Utah, and northern Arizona. Temperatures plunged 15 to 20 degrees below normal in the mountains and far interior, and 3 to 12 degrees below normal along the coasts. Forecast highs for San Diego, Los Angeles, and San Francisco were all in the 60s. Even Las Vegas was only projected to reach 82 degrees, while Phoenix and Tucson, though warm at 93, were still cooler than their late May averages. Forecasters in Los Angeles noted that the coming days would feel more like the weather in Portland than in Southern California. The cold air was even substantial enough to bring a forecast of snow to the highest elevations of the Sierra Nevada, alongside gusty winds and elevated fire weather concerns across the Great Basin. The key to understanding this continental-scale puzzle lies further south, in the fourth major effect of this pattern. A trough was digging into the Bay of Campeche and the Western Caribbean, and this feature is the most consequential for the ongoing moisture surge. This trough forms the eastern wall of the same cut-off low that was bringing cold to the west. It is not a separate system, but an extension of the same atmospheric feature. This trough represents the bottom of the U-shape that the upper-level low carves into the jet stream. As that low spins over the Great Basin, the trough extends southward and eastward, reaching deep into the tropics. From there, it lifts vast amounts of tropical moisture northward across the Gulf of Mexico and into the southeastern United States. This provides the upper-level support needed for the powerful moisture surge we have been exploring, making it the central point of this entire atmospheric story. Suddenly, the disparate weather events across the nation snap into a single, coherent picture. These are not four separate weather stories unfolding in different regions of the country. They are, in fact, four distinct surface signatures of one immense upper-level configuration. The unseasonable coolness east of the Mississippi, the record-challenging heat across the northern plains, the January-like chill in the southwest, and the drought-breaking surge of moisture from the Caribbean are all manifestations of the same omega block. They are all dancing to the same atmospheric rhythm, doing different things in different places at the same time. This profound unity means their fates are intertwined. When the block eventually breaks down, all four of these effects will dissipate together. And for as long as the block remains locked in place, all four effects will persist. The crucial question for forecasters, then, is how long this powerful pattern will hold. The forecast remains uncertain, with different models offering different solutions. Several model runs show the block persisting through the first week of June, while others project a breakdown around June 5th or 6th, as the western cutoff low is ejected northeastward into the central United States. The duration of this block has significant implications. The longer it holds, the longer the moisture surge will continue. This, in turn, means that the favorable environment for the formation of tropical cyclones in the Western Caribbean and Gulf of Mexico will also remain in place. The fate of the block and the potential for a tropical cyclone are physically coupled. If the block holds through June 10th, so too does the window for cyclogenesis. If it breaks down on June 5th, that favorable environment will change, and the probability of a storm forming after that point will depend on whatever new pattern emerges. To truly grasp the significance of this omega block, we must place it within a broader scientific context. It belongs to a class of phenomena known as atmospheric blocking patterns, which have been studied in climate literature for nearly a century. The original characterization of these patterns dates back to a 1950 paper by Rex, who identified them in upper air analyses from the 1940s. More recent research, including work by Kornhuber and colleagues in 2020 and 2023, has explored whether the frequency of these blocks is changing due to climate forcing. This line of inquiry seeks to determine if Arctic amplification, the weakening of the temperature gradient between the equator and the pole, is creating a slower, wavier jet stream that locks into these configurations more often than it did in the mid-20th century. However, the scientific community has not yet reached a consensus on this question. The literature is genuinely contested. While some studies have found a statistically significant increase in the frequency of blocking patterns over the last several decades, others have found no clear trend or have determined that any trend is regional and varies by season. The most conservative interpretation of the science is that we are still in the process of figuring out whether the blocking patterns we observe today are simply random samples from a long-term climate average, or if they represent a fundamental shift in the underlying distribution. For this reason, it would be premature to claim that today's omega block is unambiguously an event attributable to climate change, as the science does not yet support such a strong claim. But while the cause remains a subject of scientific investigation, the effect is undeniably present. Here on Calm Space, we have observed multiple high-amplitude blocking patterns just this spring. There was the wave amplification event of May 18th, which we covered as an atmospheric phenomenon unseen by anyone alive. Then came the stalled jet stream event on May 22nd, and now this omega block on May 27th. 3 distinct high-amplitude blocking patterns in just 10 weeks, all explicitly named by operational forecasters, is a high frequency by any climatological standard. Whether this frequency is simply the random walk of a stable climate system or reflects a shifted distribution is the question that science is still working to answer. But the empirical fact of this high frequency is observable, leaving us with a profound and urgent question about the nature of our changing atmosphere. To truly understand the weather across the country this week, we must look to a single, overarching feature in the atmosphere: the omega block. This one pattern is the architect of the entire continental weather story, connecting seemingly disparate events into a single, unified narrative. The unusual forecast for Memorial Day and early June, for instance, is being driven by the very same atmospheric configuration that is preparing the conditions for the first named storm of the hurricane season, which officially begins in just 4 days. The trough, drying out the Pacific Northwest, is simultaneously pumping moisture toward Pensacola, while the ridge, bringing intense heat to eastern Montana, is also anchoring the Bermuda High off the southeastern coast. Everything is connected. This pattern is unfolding over a nation that has endured 181 days of drought, a 131-year record, and is only now beginning to see relief. The convergence of this historic drought, a powerful moisture anomaly measured at 3 sigma, and the ticking clock of hurricane season makes this a moment of profound meteorological significance. While our focus remains here, it is a quiet reminder that our planet is a dynamic system of independent layers. Elsewhere, the sun is active on its far side, the Chilean subduction zone is releasing pressure, and several volcanoes are beginning new eruptive phases. While Calm Space covers all these phenomena, today's story is grounded in the atmosphere above North America. It is the story of the week when the cure for a record drought arrives on the same air mass that could spawn the hurricane season's first storm, all while other planetary dramas unfold in the background. Now, we turn to the fiery side of this atmospheric pattern. The same omega block ridge settling over the northern plains and Rockies is responsible for more than just record-challenging heat. It is also creating the most dangerous fire weather setup the country will face this week. The two phenomena are intrinsically linked. The atmospheric process of subsidence, or sinking air, is what drives the high temperatures, and this same process also causes a dramatic drop in relative humidity. Simultaneously, the anomalous height of this ridge anchors a surface high-pressure system, which in turn produces the dry, downslope winds that can rapidly spread a flame. This reveals how a single atmospheric feature can be both a source of relief and a harbinger of danger. On the morning of May 27th, the National Weather Service office in Bismarck issued a tangible expression of this threat: a red flag warning. This alert covered Divide, Williams, McKenzie, and other counties across western North Dakota. The warning detailed the expected conditions, with afternoon temperatures climbing into the lower to mid-90s, relative humidity falling to as low as 15%, and southeast winds of 25 miles per hour gusting to 40. This warning was not just for a single afternoon. The hazardous outlook indicated that near-critical fire weather conditions would persist through Thursday and Friday, as the region remained under the influence of the powerful ridge. A second, even more dramatic red flag warning was issued by the Salt Lake City National Weather Service office. This alert covered the Henry Mountains and Grand Staircase fire weather zones, designated 494 and 498 in southern Utah. Here, the technical details paint a stark picture of the risk. Forecasters projected relative humidity to plummet to between 8 and 10% on Wednesday and Thursday afternoons. This extreme dryness was to be accompanied by south winds of 15 to 25 miles per hour, with gusts reaching 40. Critically, the overnight humidity recovery was expected to be poor, only reaching 25 to 35%. This combination, single-digit daytime humidity, powerful wind gusts, and incomplete overnight moisture recovery, is what fire weather specialists define as a critical day, where conditions are ripe for potentially rapid fire growth. These are not isolated warnings, but two distinct operational expressions of the same vast upper-level ridge. The atmospheric physics are direct. The ridge produces subsidence, which dries out the boundary layer, leading to low relative humidity. The pressure gradient around this ridge generates the gusty winds. When combined with dry vegetation, this sequence creates critical fire weather conditions. It is a striking illustration of atmospheric scale that the same feature threatening International Falls with record heat is also creating an 8% humidity threat in southern Utah. They are not two separate stories, but one. This dynamic creates a profound asymmetry across the continent, which is central to the narrative of this weather event. While the eastern half of the country is receiving desperately needed drought relief, the western half is moving toward elevated and critical fire weather. For 181 days, the map of drought and the map of fire weather have been largely the same. Now, over the next week and a half, they are set to diverge. As rain arrives, the southeast and Gulf Coast will move out of fire weather concern. Meanwhile, the Great Basin, the Four Corners, the High Plains, and parts of the Northern Rockies will either remain in or move into dangerous fire conditions. The same pattern curing one corner of the country is simultaneously loading the dice in another. The operational implications of this asymmetry are significant. Should an ignition occur in this western corridor over the next 10 days, the combination of single-digit humidity and 40 mile-per-hour gusts could allow a fire to grow with astonishing speed. It is crucial to note that as of now, there is no major fire on the ground in these zones. What exists is the potential a landscape primed for a disaster, awaiting only a spark. As these terrestrial events unfold, it is worth noting other layers of activity. On the morning of May 27th, the sun was doing something quietly significant. The Space Weather Prediction Center's morning discussion noted the presence of 9 numbered sunspot regions on the visible disk. The report then grew more specific about a region not yet visible, stating that region 44747 had remained stable in its physical extent, though some minor consolidation was observed in its trailing spots. It is a subtle but constant reminder of the complex, multi-layered world we inhabit. An official report on the sun's visible face notes that while region 4452 is exhibiting rapid growth in its size and complexity, the other sunspot groups appear relatively simple and are either stable or slowly decaying. This assessment, however, only tells half the story. Another report mentions a region for which there is not enough direct imagery to perform a formal analysis. Yet, it goes on to state that data from the Sun's far side, gathered through helioseismology, points to a somewhat significant region. This particular phrasing is noteworthy, as it carries a directness not often found in the carefully qualified language of the Space Weather Prediction Center. It hints that something important may be unfolding just beyond our view. Helioseismology is a fascinating technique that allows scientists to study the Sun's unseen interior and far side by measuring acoustic waves that travel through it. Much like a seismic wave on Earth, these solar waves can reveal the structure and intensity of magnetic features, allowing for the detection of large sunspot groups before they rotate onto the visible disk. The morning discussion from SWPC implies that just behind the Sun's eastern limb, a sunspot group has been flagged by this acoustic data as large enough to warrant special mention. This region is set to rotate into our direct line of sight over the next several days, raising questions about what it might bring. Further evidence suggests this hidden side of the Sun is far from quiet. Over the last 24 hours, multiple occulted flares were observed on the northeastern limb eruptions, whose sources are still concealed behind the solar horizon. Adding to the mystery is a faint, partial halo coronal mass ejection, or CME, that appeared in LASCO C2 imagery at 22:30 UTC on May 26th. According to SWPC, this orphaned CME has no identifiable source on the visible disk, strongly suggesting its origin lies on the far side. This pattern of activity was underscored by a minor S1 proton event that peaked on May 26th. This event was driven by a large, far-sided partial halo CME, first detected by the GOES-19 coronagraph 2 days prior. Together, these clues confirm that the active region on the far side is not only real, but also energetic and capable of producing significant eruptive events. The critical factor now becomes one of geometry. As this potent region completes its rotation over the next 7 to 10 days, it will shift from being far-sided to directly facing Earth. Should it continue its eruptive behavior, the consequences would change dramatically. Its flares and CMEs would no longer be limb events with limited geomagnetic impact. They would become direct events, carrying the potential for significant disruptions to our planet's magnetic field and ionosphere. For now, activity on the visible disk is led by region 4446, which produced a C9-7 flare on May 26th. This region is classified as having an FFO beta-gamma magnetic structure, covering 400 millionths of the solar disk with 17 sunspots, and holds a 15% chance of an M-class flare in the next day. But this visible activity is merely the backdrop, the texture against which a more significant story may be about to unfold. While our attention is drawn to the Sun, the Earth beneath our feet is a reminder that our planet operates on its own clock, driven by its own physics. Over the past 24 hours, the Chilean subduction zone, the volatile boundary where the Nazca Plate dives beneath the South American plate, experienced a notable pulse of activity. A cluster of 8 earthquakes, ranging in magnitude from 4.5 to 5.1, occurred along a corridor stretching from Antofagasta to Coquimbo. While none triggered a tsunami warning or caused significant damage, 8 such events in a single day within one corridor is an unusually high tempo, even for this active region. Farther west, a magnitude 5.4 earthquake struck northeast of Nuku'alofa, Tonga, at a depth of 10 kilometers, prompting a green alert from the USGS, indicating a low probability of casualties or damage. A second magnitude 5.4 event was also registered in the Tonga region. This one exceptionally shallow, at just 3.8 kilometers deep, a common feature along the Tonga-Kermadec Trench. Meanwhile, the Fiji region produced two deep focus earthquakes, a magnitude 4.5 at 615 kilometers and a magnitude 4.9 at 535 kilometers. Though routine for this area, such deep events are always flagged, as they represent physically unusual processes deep within the Earth's mantle. The planet's restlessness is also evident on its surface. Reports from the Global Volcanism Program and the U.S. Geological Survey show a surge in volcanic activity. New eruptions have begun at Ambay in Vanuatu, Dukono in Indonesia, Kikai in Japan, Taal in the Philippines, and at the submarine Tifau Ridge in Papua New Guinea, where an eruption in the Bismarck Sea that started on May 8th continues. Alongside these new events, eruptions are ongoing at several other volcanoes, including Bezimiani in Kamchatka, Fuego in Guatemala, Mayon in the Philippines, Marapi on Java, and Kilauea in Hawaii. At Kilauea, the summit eruption within Halemaumau crater has been marked by episodic fountaining and incandescent spatter. In the United States, 4 monitored volcanoes are at elevated alert levels. Great Sitkin in the Aleutian Islands is on watch orange, the second highest aviation alert, while Kuprianov, Shishaldin, and Kilauea are all on advisory yellow. These events, the hidden activity on the Sun, the seismic cluster in Chile, and the volcanic stirrings across the Pacific, are not the central story of the week. They are independent layers, each unfolding in parallel according to its own physical laws and timelines. They are not connected to the atmospheric patterns over North America that are bringing both drought relief and the season's first hurricane threat. We include them because a true understanding of our world requires acknowledging all its dynamic systems, not just the one currently holding our focus. Here on Calm Space, we believe in exploring all these interconnected layers. We have previously examined the science of far-side solar detection and the intricate dynamics of the Pacific Ring of Fire, and we will return to these subjects when new data warrants a closer look. For today, they serve as vital context. In the same week that a single air mass brings both a cure for a historic drought and the threat of a hurricane, the sun is preparing a surprise on its hidden face. The Chilean coast is trembling in a rapid sequence, and 5 volcanoes are awakening around the Pacific. The atmosphere is not the only system in motion. With this wider context established, we return to the primary narrative, having explored both the cure and the impending threat. We have now charted the complex interplay of factors at work, the social media noise that can obscure the picture, the ensemble signals that confirm it, the broader atmospheric context that frames it, and the independent meteorological layers operating beneath it all. This brings our exploration to its final, central question, one this entire analysis has been building towards. It is a question I hope you will carry with you long after this script concludes, as it is one this Calm Space community is uniquely suited to contemplate with honesty. Can a nation truly afford a cure when that very cure carries with it a significant threat? Let us begin by visualizing a map of the southeastern United States and the Gulf of Mexico. On this map, we would shade every reservoir, every aquifer, and every river system that has registered below normal levels for the last 181 days. We would then highlight each county operating under a drought response declaration. We would mark the winter wheat fields, where only 30% are rated as good to excellent. We would also identify the cattle ranches within the 61% of U.S. cattle areas currently experiencing drought, a sharp increase from 31% just 1 year ago. Finally, we would color in every community in Florida, Georgia, Alabama, Mississippi, and Louisiana that has watched the U.S. Drought Monitor map turn a deeper shade of red with each passing week since January. This composite image is a map of profound need. It shows us who requires the rain and who, by Saturday, will begin to receive the first meaningful relief of the year. Now, let us overlay a second map onto the first. This time, we will mark every coastal county from Brownsville, Texas, through the Florida Keys and around to the Outer Banks of North Carolina. We will highlight every barrier island community, every designated flood zone neighborhood, every storm surge zone, every evacuation route, and every emergency management facility. This second map is a geography of vulnerability. It reveals who bears the cost if a tropical storm were to organize within the very same moisture envelope that is delivering the desperately needed rain. The overlap between these two maps is substantial. The Gulf Coast that needs the drought relief is the same Gulf Coast that would pay the price for early season cyclogenesis. The Florida that is parched for rain is the same Florida the storm would likely strike. The nation, it seems, cannot receive the cure without also embracing the threat. This paradox is the central thread of our story. We have reached the point where we must ask with sincerity whether the country can afford this trade-off. It is a question that demands an honest assessment of the costs and benefits, as clarity matters far more than rhetoric when the stakes are this high. The advantages of the coming moisture surge are undeniable. The drought has been tracking along a 1-3-1-year record trajectory, with the third driest single month of any season ever recorded, sitting behind only the climatological peak of the Dust Bowl. The agricultural sector is emerging from this dry phase with the lowest winter wheat good to excellent rating on record, the smallest winter wheat acreage since 1919, and 61% of its cattle areas in drought. The arrival of significant rain across the southeastern Gulf Coast over the next 4 days, even if it doesn't end the drought entirely, is an unambiguously positive development for the food system, for rural communities, for state economies, and for the year's climatological outlook. If the rain persists, drought declarations in Florida and Georgia might be relaxed in weeks rather than months. The risk of fire across southeastern zones will drop as live fuel moisture is replenished. River systems like the Pearl, the Wolf, the Calcasieu, the Aransas, Oso Creek, and the Saluda will begin to re-establish the base flow they have been losing for months. When the U.S. Drought Monitor map updates next Thursday, it is expected to show pockets of improvement in places that have only deepened in color for half a year. However, the costs associated with this moisture surge are just as real, and they are already beginning to manifest. The first 3 inches of rain falling on soil baked hard by drought create disproportionate runoff and a rapid flash flood response, a phenomenon we can already see in the river gauge data. As of this morning, the Houston and New Orleans metro areas, the mobile Pensacola corridor, and parts of the Mid-South and the Ohio Valley are all under flood watches or warnings. Flash flood warnings in Dallas, Ohio, and West Virginia have already been verified within hours of being issued. The rain is not arriving as a gentle, multi-day soaker, but in intense convective bursts, delivering 2 to 3 inches at a time. Under such a deluge, surface drainage systems in much of the southeast are expected to back up. This is not a hypothetical risk. It is an unfolding reality. The operational forecast for the next 48 to 72 hours includes local damage, displaced families, and potentially even fatalities. And then there is the question of the storm itself. The window for possible tropical cyclogenesis, according to ensemble models, is from June 1st to June 10th. The probability of a storm forming ranges from a conservative 6% on one AI model to 20% on the European spectral model. A central estimate of 10 to 15% might not seem high, but it is far from zero. In fact, a 10 to 15% chance of a named storm in the first 10 days of June is roughly 7 times the climatological base rate for that period, which makes the signal quite real. This probability is high enough that the National Hurricane Center will begin monitoring the area closely starting Friday or Saturday. It is high enough that the Air Force Reserve hurricane hunters will be placed on standby for reconnaissance flights next week. And it is high enough that emergency management agencies along the Gulf Coast are already running tabletop exercises this weekend for a low-end tropical storm landfall scenario. The cost of this threat materializing would be on the order of a low-end tropical storm, several $100 million to a few $1 billion in damage, a few dozen to a few hundred displaced families, and a news cycle that would dominate for about a week. The cost of the threat not materializing, however, is zero in dollar terms. This raises a complex calculus of risk and reward, because the moisture surge delivers its life-giving rain whether or not it organizes into a cyclone. So, can the country afford the cure? The most honest answer is that the country has already accepted the cost, because that cost is structural. We have a coastline, we have a hurricane season, we have a Gulf Coast that is geographically situated precisely where early-season tropical systems tend to form. The nation accepted the cost of this geographic reality when it built cities like New Orleans, Mobile, Pensacola, Tampa, and Miami, placing hundreds of billions of dollars of infrastructure in zones vulnerable to storm surge. The country accepted the cost of the cure when it accepted its own position on a continent adjacent to an ocean basin that produces tropical storms every year. The fundamental question, then, is not whether the country can afford the cure. The question is whether the country is prepared to receive it. As unusual weather patterns unfold, they often give rise to compelling narratives, and it can be helpful to explore some of these ideas as we navigate the weeks ahead. These perspectives will likely feature prominently in online discussions, so addressing them with clarity can provide a useful foundation. One prominent framing suggests that the recent surge of moisture, which is helping to alleviate drought conditions, might be an engineered event. The timing arriving just 4 days before the official start of hurricane season can appear suspiciously convenient, leading to speculation that technologies like HAARP, cloud seeding, or other classified geoengineering programs are responsible. However, when we examine the physics of our atmosphere, a different picture emerges. One rooted in the immense energy budgets of planetary weather systems. Continental-scale rainfall is governed by powerful upper-level dynamics, such as the behavior of the jet stream, the geometry of Rossby waves, the position of the Bermuda High, and the influence of the Madden-Julian oscillation. These processes operate on an energy scale that is simply staggering, approximately 17 orders of magnitude greater than any weather modification technology humans currently possess. For context, the High-Frequency Active Auroral Research Program, or HAARP, operates at 3.6 megawatts. In a single hour, a typical Rossby wave involves energy transfers on the order of 10 to the 25th joules. The disparity is not minor. It is a fundamental difference in scale that underscores the power of nature. While cloud seeding can locally enhance precipitation from an existing storm by 5 to 15%, it cannot conjure a continental moisture surge from the Caribbean. The current drought relief is occurring in concert with a well-documented favorable phase of the Madden-Julian oscillation and a specific Bermuda High position natural phenomena doing exactly what they are known to do. Another perspective that has gained traction implies that the National Hurricane Center might be concealing a more alarming forecast. This idea suggests that the official outlook of no formation expected in the next 7 days could be a deliberate downplaying of the true risk. Yet, a closer look reveals that the NHC's forecasting process is one of the most transparent operations within the US government. All of their products are made public, and the detailed text discussions are signed by the on-duty forecasters, such as Berg and Reinhardt, or Brown, Brennan, and Kangloy on other shifts. This accountability is a core part of their mission. Furthermore, the foundational data they use, sea surface temperature analyses, European and GFS ensemble models, wind shear data, and Madden-Julian oscillation diagnostics are all independently available from non-NHC sources. Anyone with an internet connection can access this underlying data and verify the NHC's conclusions for themselves. The fact that three distinct ensemble systems independently converge on a low probability signal for development between June 1st and 10th serves as its own verification. The NHC accurately communicates this as a low probability of development possible later in the window. They are not hiding a forecast. They are carefully communicating scientific uncertainty, a practice that can be misrepresented by hype-driven channels, because nuance often generates fewer clicks than alarm. This leads to a broader claim, that the forecast models themselves are intentionally manipulated. This narrative posits that major institutions, like the European Centre for Medium-Range Weather Forecasts, the UE, National Weather Service, and even Google's DeepMind, are coordinating to either suppress or inflate forecasts for some hidden purpose. The response to this lies in the very structure of these organizations. We are talking about three independent bodies, located in two different countries, each with fundamentally different institutional incentives and entirely separate mathematical architectures. A coordinated falsification of data across these groups would demand a level of cross-institutional and cross-architectural collusion that has no historical precedent and no plausible mechanism. The simpler explanation is almost always the more likely one. In this case, three independent systems are detecting a faint but real signal in the atmosphere during the same calendar window because the underlying environmental conditions genuinely support that possibility, regardless of the specific methodology used to model it. When independent methods arrive at a similar conclusion, it generally strengthens confidence that the signal is real, not manufactured. A fourth framing, which has appeared in the comments on Calm Space, suggests the sequence of drought, fire, heat, and hurricanes is a great reset event designed to engineer scarcity. This perspective deserves a direct look, as it is born from genuine and observable conditions. The record drought, agricultural stress, extreme fire weather, and anomalous temperatures are all real. The ENSO transition and 3 sigma moisture anomalies are measurable facts, not fabrications. The error in this framing is not in the observation, but in the causal attribution. These conditions are not the product of a coordinated scarcity campaign. Instead, they are the result of documented Rossby wave amplification occurring on top of a 1,300-year mega-drought baseline. A credible, though still debated, amplifying factor may be what is known as the Hansen aerosol unmasking hypothesis. This convergence of extreme events is not a secret plan. It is precisely the kind of outcome that climate science literature has been forecasting for the past 2 decades. For viewers who feel that something is being done to them, the most honest answer is that the climate system itself is doing it, driven by cumulative greenhouse gas forcing, combined with factors like the 2020 maritime fuel sulfur cap. The true engineering question is not how to stop the climate, but how we can adapt to its changing outputs. Finally, on the opposite side of the spectrum, there is a hopeful narrative suggesting that the developing El Niño will fix everything. This idea also warrants a closer look. The effects of an El Niño signal are subject to significant lags. The Pacific Ocean does not simply flip a switch and immediately end a drought in the southeast or refill reservoirs in the west. Forecasters face what is known as a spring predictability barrier, making it difficult to be certain about the strength and timing of any projected El Niño. Historically, if relief from El Niño does materialize, it typically arrives in the late autumn or winter. Even then, its benefits are geographically specific, often concentrated in atmospheric river events over California, beneficial rains for Texas and the Gulf Coast, and a wetter southern tier overall. However, the southeast, including Florida and Georgia, is not guaranteed relief from El Niño's standard teleconnection pattern. For these regions, relief during the spring and summer of 2026 will depend far more on the kind of tropical activity that the early June ensemble window is hinting at, not on a distant El Niño. This brings us back one last time to the social media hype cycle, which is important to reflect on as we conclude. The channels that began promoting sensationalist thumbnails on Monday are not just mistaken about the timing of a potential storm. There is a common misconception about the fundamental purpose of hurricane forecasting. Its true value is not in generating alarm, but in facilitating critical decisions when faced with events that are low in probability but immense in consequence. This is the science that allows emergency managers to decide whether to preposition generators, and it guides state agriculture departments in authorizing an early harvest. For coastal county sheriff's departments, it informs decisions about updating evacuation routes. And for the residents of low-lying areas, it helps them decide whether to move their boat into the yard. Real hurricane forecasting provides a clear understanding of the actual probability of impact, clarifies the next decision point, and outlines the consequences if that probability unfolds unexpectedly. This is a discipline that trades on its credibility. In contrast, some channels can burn through that credibility for the sake of engagement, producing breathless content week after week about systems that never even materialize. This constant cycle of alarm can have one of two damaging effects. The audience may become desensitized to legitimate warnings, or they may develop a persistent anxiety about events that never occur. Either outcome is a disservice to the people who rely on accurate forecasts when a genuine storm finally appears. If a storm, which might be named Arthur, does take shape, the data suggests it will form during the first week of June within the very moisture envelope we have been tracking. It would likely be a low-end tropical storm, and its path would probably lead to a landfall somewhere along the Gulf Coast or in Florida. For a region that desperately needs the rain, it would likely deliver a significant break in the ongoing drought. The system would probably dissipate within 4 days of its formation, making headlines on local newscasts in places like Tampa and Pensacola for a few nights before fading from the national conversation. This single event, however, is just one piece of a much larger puzzle. The question of whether 2026 will be a front-loaded season or one that is suppressed throughout will remain unanswered after this storm passes. One named storm simply cannot provide that answer. The true character of the season will be revealed by what happens or doesn't happen in July, August, and September, as the El Niño transition either accelerates or stalls, and as the Atlantic basin either builds on its early activity or quiets down under increasing shear. What we can say with confidence today, on the 27th of May, 2026, is what the immediate data shows. A historic drought is beginning to break as the atmosphere delivers long-awaited relief. This relief is arriving within the same air mass that the world's major weather models are monitoring for potential tropical development. It is a profound atmospheric duality. The cure for the drought and the potential threat of a storm are contained within the same body of air. The country cannot receive one without the possibility of the other. Many narratives may misrepresent the timing, the meaning, and the magnitude of what is unfolding. In the coming week and a half, as the noise continues to build, it becomes essential to find a clear signal. Here at Calm Space, our commitment is to be that filter for you, to tell you when the signal truly becomes the story. The next time we speak on this, the hurricane season will have officially begun. As we look toward that future, it unfolds as a tapestry of possibilities. There may or may not be a storm in the Western Caribbean, and it may or may not bear a name. The Omega block that has influenced recent weather may or may not remain locked in place. The northern plains could still be experiencing temperatures of 100 degrees Fahrenheit in early June, or they could cool. A region on the sun's far side which has been active may rotate onto the visible disk and begin producing direct eruptions, or it may not. The Chilean subduction zone could produce another cluster of magnitude 5 earthquakes, or it could remain quiet. The food system, the water system, the fire system, the climate system, all of these are vast and complex, each operating on its own clock. We will be here to observe whichever of these clocks chimes first. But for today, the story is this. The worst drought in the modern record is starting to recede. The first substantial moisture of the year is flowing across the southeast and the Gulf. The hurricane season officially opens in just 4 days. And at this very moment, 3 independent ensemble systems are converging on a low probability signal for tropical development, located inside the same air mass that is breaking the drought. The cure and the threat are one and the same. The country has been waiting 181 days for this rain, and now the rain is here. What comes with it is simply what comes with it. In a way, what replaces the drought is a new kind of challenge, not because rain is worse than drought, but because the atmospheric machinery delivering this relief is the very same machinery that opens the next chapter. That next chapter is the hurricane season, and it begins atop an El Niño Southern Oscillation transition that no one can fully predict. The country that has been waiting for the rain must now live with what comes next. This is what we know. It is what the data, the models, and what the National Hurricane Center are all saying when they state that formation is not expected in the next 7 days. And it is what the European Center, the GFS, and Google DeepMind are alluding to when they suggest possible development is on the table for the period between June 1st and June 10th. This is where we stand. As one chapter of waiting ends and a new one begins,